Chapter 12, we're looking at kinetics. Kinetics in chemistry looks at how fast things happen. So we're looking at the rate of reaction. So rate of reaction is how fast a reaction proceeds. So if we're looking at a reaction of hydrogen plus oxygen going to water, we can look at how fast this rate occurs in a couple of ways. One way we can look at it is to look at how fast reactants are used up and the amount of time that happens. And so we're looking at the change in concentration over the change in time. A here would be the concentration of one of the reactants. Another way we can look at the rate of a reaction is to look at how fast a product is being created in a certain amount of time. So again, it's going to be the change in concentration over the change in time, but this time it's a change in concentration. For our reaction rate where we're looking at the reactants being used up, usually that's going to be a negative because that concentration is decreasing. If we look at the concentration of a product, that's going to be positive because the concentration of the product is increasing. Some reactions are slow, some reactions are fast, and you really can't tell by looking at the chemical reaction which it is. If we look at the reaction between sodium hydroxide and hydrogen chloride, if we look at an aqueous solution of each, then we get sodium chloride and we get water. That's a very fast reaction. One of the reasons it's so fast, if we're dealing with solutions, sodium ions and hydroxide ions are already present as building blocks, as ions. So is the hydrogen ion and the chloride ion in its solution. So it's very easy to just assemble particles, and in this case we're just assembling water, H2O, because the sodium ions and the chloride ions stay as ions if we're dealing with the solution. If we're looking at solid magnesium with hydrogen chloride, again a solution of hydrochloric acid, it's also a fairly fast reaction. You see the bubbles happening essentially instantly when you put magnesium into hydrochloric acid. So you're getting hydrogen gas liberated, and the magnesium ions and the chloride ions again stay as ions. If we look at the bottom reaction, we have methane plus oxygen forming carbon dioxide and water. Now just in the room temperature, 20 degrees is roughly room temperature. If you have methane gas in contact with, in the same container with oxygen gas, you will get a reaction and you will produce carbon dioxide and water vapor. It just goes really slowly. The gas we have in the Bunsen burners is methane, and it goes a whole lot faster, but that's no longer at room temperature. So if we look at kind of the general characteristics of rates and what makes them fast, ionic compounds that are dissolved in water, as I said before, tend to be really rapid reactions. The anions and the cations are already dissociated, and so all you have to do is put them together. In terms of steps that we're going to look at for a reaction proceeding, first of all, the positive ions, the negative ions, anions and cations, are hydrated. Water attaches to them. If you look at the picture on the right, we have the sodium ion here. It's positive. It is attracted to the negative end of the water molecule. And so we're actually going to have several water molecules surrounding each sodium ion. So these hydrated sodium ions now move around in the solution. They rotate, they spin, they kind of expand and contract, and they bump into other ions. Sometimes they're the positive sodium ions that are hydrated, sometimes negative ions that are also hydrated. And if they come in contact with a negative ion, and if the attraction between the sodium ion and the negative ion is great enough, then we'll get an ionic compound. But we're only going to see a compound formed. We're only going to see a reaction if we either get a precipitate, and then it's going to fall to the bottom, or solution gets cloudy, or we get a gas formed. If we have a combination of two solutions where we get no precipitation or we get no gas formed, there's really actually no reaction going on. When we look at covalent compounds, it's a little bit more challenging. They tend to be slower because first of all we have to break the bonds, and then we have to reform them, mix them around, reorganize, reposition everything, and then reform them. So covalent compound chemical reactions tend to go more slowly. Collusion theory is the way that we try and explain what's going on in our reaction containers, in our beakers, in our test tubes. And the collision theory really describes what's going on depending on the collision of the particles. And not all particle collisions create a chemical reaction. Only collisions with a certain amount of energy and the correct orientation are going to react and form something new. If we increase the number of collisions, we get a faster product formation. We get an increase in the rate of a reaction. There are a couple of ways we can increase the number of collisions. One way, we can increase the concentration of the reactants. And this works for liquids and it works for gases. We have more molecules moving, which means more chance for collisions and therefore greater rate. So just by sheer numbers, we can get those collisions going on. We can get a faster reaction rate. For solids, if we increase the surface area, we can do that by crushing up our solid, by stirring a solid in a solution, by mixing solids together. We increase the surface where those particles can make contact, where effectively collisions can occur, and that's going to increase our reaction rate as well. Okay, another way we can increase the rate of a reaction is to increase the temperature of our reaction vessel. This actually does two things. First of all, we give the particles more kinetic energy, so they're going to move faster. What that does is it increases the number of collisions per unit of time that are happening. Second of all, that increase in kinetic energy means when those particles collide, they collide with more energy and are more likely to have enough energy on their collision to cause a reaction to happen. If you remember, when we started this, we said that the rate of reaction depends on the orientation of the collisions and the number of collisions. It turns out for temperature increase, there's actually a measurable and predictable amount the rate will increase as you increase the temperature. So if I increase the temperature by 10 degrees, I'm actually going to double the rate of the reaction. So if I look at the chart that's sitting there, if I go from 25 degrees Celsius to 35 degrees Celsius, the amount of time it takes for that reaction to happen is half as much because the rate is going twice as fast. It works the other way as well. So if I drop the temperature by 10 degrees, so going from 25 to 15 degrees Celsius, then my reaction time is going to double because my reaction is proceeding half as slowly. Another way that I can change the rate of a reaction is for gases, I can increase the pressure. And by increasing the pressure, it's the same as for solids and liquids increasing the concentration. I have more particles colliding. Usually, if the volume is the same, then the particles have less room per particle. So the likelihood that they're going to run into other particles in the container vessel is increased, so the reaction is going to happen more quickly.